in this video I'm going to be talking about basis and dimension. And so I'm going to start with some definitions. And for all these definitions, we're just going to suppose that W is a subspace of Rn. And what we'll say is that if the span of a set is equal to W, then that set spans W. This is using span as a verb. For example, the set S equals I, J, and K, that set spans all of R3. Because we know that we can make any vector in R3 as a linear combination of I, J, and K. And we could call S a spanning set for W. And these things together, they kind of lead us to the idea of the basis, which is, and we'll say that a basis for W is a spanning set that is also linearly independent. Okay? So it's somehow a minimal spanning set. And we'll see how this works in a few minutes. Back to the example of S equals I, J, and K. That's a linear independent set, right? We know that none of those three can be expressed as a linear combination of the others. There's all sorts of reasons that we know that S is independent. And since it spans R3 and it's linear independent, I'm going to say this is a basis for R3. In fact, it's the basis we're going to use so often, it's the basis you use in physics, right? You talk about vectors in terms of as a linear combination of I, J, and K. It's what we would call the natural basis. All right, so let's work an example. Let's find a basis for the null space of A. Now, I'm sure you remember that when you are asked about the null space of A, you are thinking about the solutions to the equation AX equals 0. And so what we're going to do is we're going to take A, we're going to augment it with 0, and we're going to row reduce. Okay. And what I think I'm going to do, I think I'm going to just kind of quickly do the row reduction, and I'm not going to make you watch me do it. And so I started by subtracting 2 copies of row 1 from row 2 and 1 copy of row 1 from row 3. Then I used row 2 to kill off row 3 and added 1 up onto row 1 to clear out the second column. And then I took row 2 and multiplied it by -1 to get the matrix into reduced echelon form. Okay. But what this is telling me, interpreting my solution space, is going to be, I'm going to need to clear some of this stuff out. That's much better. And so I'm going to, start saying, well, this is telling me that x1 plus 2x3 plus 3x4 is equal to 0. And that x2 plus x3 plus 2x4, wait a second, that needs to be a -2. Yeah, that doesn't seem right. Minus 2x4, that equals 0. Yeah, when I multiplied the second row by -1, I forgot to multiply that last entry. All right, and so I can say that these two things together tell me that x1 is equal to -2x3 plus 3x4. No, minus 3x4, I'm keeping that same error. x2 is going to be equal to -x3 plus 2x4. And x3 and x4 are going to be independent variables. They can be whatever they want. And then this kind of tells me that my solutions to ax equals 0 kind of take the form x equals -2x3 minus 3x4, -x3 plus 2x4, x3, and x4. Now I could kind of split this out over the x3s and the x4s and write it as the sum of two vectors, right? And so I could say this is equal to Okay, in terms of x3, I've got negative 2 x3s here, negative 1 x3s, x3, and then I don't have any x3s in the fourth component, so I'm going to put a 0 there. And I'm going to add that to, I'm going to add that to, okay, the stuff with x4, that's negative 3x4, positive 2x4. I don't see an x4 in that third spot, so I just put a 0, and I'll put an x4 there. Okay? And these are all of the vectors in the null space can be expressed this way, right? Based on the row reduction and the interpretation of the solution and all this stuff. Okay, now what I'm going to do is I'm going to factor the x3 and the x4 out of those two vectors. And I'm left with, you know, some number of negative 2, negative 1, 1 zeros plus some other number of negative 3, 2, 0, 1. And what that means is that every vector in the null space can be expressed as a linear combination of these two vectors right here. This negative 2, negative 1, 1, 0, and this negative 3, 2, 0, 1. Which means that those two vectors span the null space. They are linearly independent, so they are going to be a basis. Okay? They are linear independent specifically because there's only two of them and they're not a multiple of each other. But you know, you could go and convince yourself other reasons why they have to be linear independent. But I'm going to say that the basis for the null space that I was hoping to find is the set that has these two vectors in it. So negative 2, negative 1, 1, 0, and negative 3, 2, 0, and 1. And that's how we find a basis for the null space. Right, now I want to talk about dimension. So if we've got a basis, if B is x1, x2, all the way through xp is a basis for subspace W, then we'll say that the dimension of W is equal to P. The dimension is the number of vectors in a basis for that subspace. And, well, this is definitely, you know, the definition of dimension that we want to use. Dimension is still exactly what you expect it to be. The dimension of a plane is going to be 2. The dimension of a line is going to be 1. The dimension of R5 is R5. It'll work like here. And here are some theorems that you might end up wanting to use at some point. I'm not going to prove them for you in this video. I'm going to do that separately, you know, maybe next time I see you in class or something like that. But I will kind of read them out to you. If we've got a p-dimensional subspace W, then any collection of more than p vectors in W has to be linearly dependent. And that's going to be true. We've already seen that. We've seen that, you know, any collection of 4 3-dimensional vectors has to be linearly dependent. And we know that the dimension of R3 is 3, so it kind of makes sense. And a corollary to that theorem is that every basis for a given subspace W has p vectors in it. Okay? So there's only one dimension for a given subspace. It's kind of like a different way of saying that. And then the next one, I think that the number 1 is pretty self-evident, that if the dimension of W is p, then any set of fewer than p vectors, it can't span all of W, right? If you have 2 3-dimensional vectors, those 2 vectors, they can't span all of R3, right? They're going to span a plane within R3, but they can't fill up all of W, or all of R3 in that case. Or any set of p linear independent vectors in W is a basis for W. That one, I think, would require, you know, a little more. Like, how do you know that p linear independent vectors in W, which has dimension p, will span all of W? That's a good question. That's something that we would need to dive into. And that any set of the right number of vectors that happens to span W will automatically be a basis for W. That's another one that we're going to have to dive in and you know, prove to ourselves. Okay. Now the rank nullity theorem is something that we're going to talk about in one of the next videos. But I thought I'd, you know, while we're talking about dimension, it makes sense to introduce the concept of rank and nullity. Now rank is something that we have actually already kind of seen or talked about in this class. We just haven't used that word. Okay, so the rank of a matrix, of an m by n matrix, is the dimension of its range. Okay, it is also going to be the number of pivots in the reduced echelon form of matrix A. Okay. The nullity is going to be the dimension of the null space. So for that example that I worked earlier, where I had that 4 by 4 matrix, or maybe it was 3 by 4, I don't remember. Let's go back and look. Yeah, it was 3 by 4, and I saw that the basis for the null space had 2 vectors in it. This basis right here, there were 2 elements. So what I would say is that the nullity of matrix A is equal to 2. Okay. I'll also say, because I can see that there were 2 pivots in the reduced echelon form of A, that the rank of A is also going to be 2. And then the fact that the rank and the nullity are kind of complementary and that they add up to the number of columns, that's the rank nullity theorem, and I'll tell you about that sometime soon. Now, the last couple of pieces of information I need to relay to you are a couple more theorems. Is that if we've got a square matrix that's non-singular, then it has rank equal to n, right? It's got full rank. It's got the maximum possible amount of rank. Because it has all the pivots, right? All the pivots sit along that main diagonal. We know how it's going to go when we row reduce a non-singular n by n matrix. Okay, so I think that this should not be terribly surprising. Now, this one, on the other hand, every year when I come into contact with this one, I find myself initially like surprised by this. Like, wait a second, like, why is this true? And again, I'm going to prove none of these theorems for you in this video. That'll be something for a different time. Maybe the next video, maybe a couple from now. But a matrix is going to, and this is not necessarily a square matrix. Okay, so this is an m by n matrix. The rank of the transpose is the same as the rank of the original. And if you think real hard, you can probably see how that's going to be true in terms of the pivots and the row reduction and how that's going to happen. But I think that this is something I want to prove for you, kind of in its own right. And the last thing is going to be a corollary to that theorem, which is that the dimension of the row space of A is actually the same as the rank of A. Which, is the same as saying A and A transpose have the same rank. Now, I know we haven't talked a whole lot about row space yet, but it's something that we will touch on as we continue to move through the course. The row space of A, oftentimes abbreviated row of A, is equal to the range of A transpose, is kind of generally how we find it. Now, I'm going to show you a couple more theorems in the next video, the range tricks and the row space tricks, that are really going to help us, write down a basis for range and row space real quickly. But for now, you could compute the row space by turning a matrix on its side and computing its range the old way, which was kind of annoying, but it was very workable. Okay? And so I think that's all of the facts that I need to tell you about basis and dimension. And so that'll be all for this video.